In this video, we're extending the power rule for derivatives to work for negative exponents. So just a reminder of our prior result for positive exponents. If I have a function that looks like x to the n, then the first derivative of that is going to be nx to the n minus 1, provided that that exponent was a natural number, in other words, a positive integer. Now our goal is to prove that the same rule works even if n is a negative integer. So we still get the same form, nx to the n minus 1, even if n happens to be a negative integer. And this is going to allow us to differentiate functions like x to the negative third, for example, which we could write as 1 over x cubed. So to start our proof, we're just going to let our function f of x be equal to x to the n, where n is a negative integer. But we can quickly write this in terms of a positive integer, which is the thing that we already understand from our prior result. So using the properties of exponents, I can write this as 1 over x to the negative n, and negative n is actually a positive integer because n is a negative integer. So now it's going to make everything a lot cleaner if we give a name to this positive integer. So we're going to let m equal negative n. And note there again that m is a positive integer because n is negative. So now we can write our function as 1 over x to the m. And that m is a positive exponent. We know how to differentiate x to the m if we need to because we have our prior result for the power rule. Now another tool that we just recently got was the quotient rule. We know how to express the derivative of a fraction in terms of the derivative of the numerator and the denominator. So we're going to apply the quotient rule to 1 over x to the m. And the quotient rule is probably the ugliest rule we've gotten so far, and this is how it turned out. You take the derivative of the original numerator. So I just wrote that in there as a 1 prime. So I know the derivative of a constant is 0 and that whole term is going to vanish, but I'm just trying to be complete with the quotient rule for a second. So I have a 1 prime times the original denominator left alone, and that was x to the m. And then we subtract a term where we have the numerator left alone times the derivative of the original denominator. So I have an x to the m prime. I still need to differentiate that guy. This is all divided by the original denominator squared. Now remember, this whole first term is going to die because the derivative of a constant is 0. And as we do the next step, I'll go ahead and differentiate x to the m. This is the moment where we use our prior result that the derivative of x to the m is mx to the m minus 1. So our numerator comes out to negative m x to the m minus 1, and our denominator, that was x to the m raised to the second power, that gives us x to the 2m. Now we can use exponent properties again, and we're just subtracting a 2m from the exponent of x up there in the numerator. Well, that gives us negative m x to the negative m minus 1. And now we're about to complete the proof. Remember what m stood for. Over here is where we made the substitution, m equals negative n. So let's replace all the m's with negative n's, and that's the moment we get what we were looking for. Even when n is a negative integer, the derivative follows the exact same pattern. I get nx to the n minus 1, and that completes the proof. So we tack on a little box, which is equivalent to saying QED, or that's the thing we were trying to prove. All right, so now that we know the power rule works for negative exponents, let's put this into practice by solving a couple quick examples. So we're asked to compute the first derivative of each of the following functions. The first one is 1 over x to the 5th. The second one is a little more complicated. It's a product of 1 over x squared and x plus 1. So in our first example, we're differentiating 1 over x to the 5th. And we need to recognize this as a power function with a negative integer exponent. So we're going to rewrite this as x to the negative 5th. So now we use the fact that the power rule works for negative integer exponents. We just bring that exponent down in front and subtract 1 from the original exponent. And we could say that's our final answer, but it's not really in the nicest possible form. So generally we're expected to write our answers in terms of positive exponents. And I'm going to re-express that as negative 5 over x to the 6th. And that example is done. Now in the second example, there's a couple ways we could go with this. We could apply the product rule here, but I think it's a little bit simpler if we just go ahead and distribute the 1 over x squared into those parentheses. So we're going to modify f of x by distributing 1 over x squared into the parentheses. So when I multiply that by x, one of the x's cancels, leaving me with a 1 over x. When I multiply it by 1, of course, I just get a 1 over x squared. Now you need to recognize that each of these things is expressible with a negative exponent. So the first term could be written as x to the negative 1, while the second term could be written as an x to the negative 2. Now we can use our new fact that the power rule works for negative integer exponents. So we bring the exponent down in front on the first one, so that's just the minus sign in front, and subtract 1 from the original exponent. We do the same thing for the second term, so we bring the negative 2 down in front and subtract 1 from the exponent. So we have negative x to the negative 2 minus 2x to the negative 3. Again, that answer is considered suboptimal. We want to express this with positive integer exponents. So I'm going to rewrite it as a negative 1 over x squared minus 2 over x cubed, and we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.